Welcome back to Pinewood Studios. What we're going to do today is we're going to have a quick look at conservation of energy. Okay, now we're going to look at it from a GCSE point of view, so this might be sort of P1 physics, if you do AQA syllabus, something you'll probably do at some point in GCSE physics at least once. Now, energy is vitally important, and the transfer of energy is how everything that you recognise as an event happens. So, for example, if we look at our bulb, you might recognise this from my last video. This bulb is currently transferring electrical energy from the power pack into heat and light energy. Okay? Now, if nothing ever transferred energy, nothing would ever happen. Okay, so one possible way the universe will end is when everything reaches the same energy level, that's it. It will just be in a state of constant stasis. Nothing else will be able to happen. Okay? But what does the conservation of energy mean? Well, the conservation of energy means whatever energy we put into something, we get the same total energy out. So looking at our bulb, for every 100 joules of electrical energy we put in, the amount of heat plus light we get out will add up to exactly 100 joules. Okay? Not a joule more, not a joule less, exactly 100 joules. Okay? Now, that's true of every single energy transfer. Whatever energy you put in, you always get the exact same amount out. But it might not always be the type of energy that you want. And so what we sometimes need to do is we need to transfer, or we need to rather represent energy transfers using something called Sankey diagrams. Now, I'm a physics teacher. I see great value in learning physics. If you think of our modern world, without a knowledge of physics, it would be nothing like what we are used to. However, Sankey diagrams, I have to admit, are my absolute pet hate. I don't see the point in them, other than they're on your GCSE syllabus. So if we think about our bulb, we are putting electrical energy in. So if we were to draw a Sankey diagram of a bulb, we would represent that with a nice vertical rectangle. Now, the only thing that matters in a Sankey diagram is the height of the box here, and as we'll see, either the height or width of the arrows in a minute. Now, with our bulb doesn't give us a large proportion of light, okay? So only a small amount of electrical energy turns into light. That's the useful energy we want out, so we represent that as going straight across, okay? The rest of the electrical energy will be turned into heat. And as you can see, there's a bigger proportion of heat because this height here shows us what proportion of the electrical energy has been turned into heat. Now, usually at GCSE, the waste energy is shown curling downwards to show it's not being transferred usefully. And the trick is that the width of the arrow at these 2 points here and here should be the same as the height of this bit of the box here to here. Okay? Now what you need to do with Sankey diagrams is you need to work out what scale it is. It's kind of like a bar chart, but going horizontally instead of vertically. Okay? So suppose this was 10 centimeters and represented 100 joules. What you could do is you could then work out how many joules each centimeter represents. You could then measure this distance here for the light and work out how much energy has been converted to light. You could then work out this distance here and work out how much energy has been converted to heat. So how far along the arrows go, or how far it curves down, is irrelevant. It's simply the proportion of these two heights here which show the proportion of the split of the original amount of energy. Now notice there's no gaps between the light and the heat arrows because the amount of energy out has to exactly equal the amount of energy in. Okay? In this case, the light is useful. So we could work out the efficiency of the bulb because efficiency is the useful energy divided by the total energy in. And that's a formula that's on your formula sheet. Okay? Now some people have been complaining in my videos there's never been any experiments. So I like to call this the possibly breaking my iPad experiment to demonstrate conservation of energy. What I'm going to do is I'm going to secure it in between two carefully prepared stands. Let me show you that setup. Yeah? So there's one stand, I'll clamp on it, There's the other stand with a clamp on it, okay? Now, there's lots of great things to enjoy about being a science teacher. My particular favourite is when you ask a kid, or a student, is the correct word we should use, I suppose, to go to the prep room to collect a long stand, okay? And then they just go there, and if you've arranged it with your technician in advance, the technician will just make them stand there for 10 minutes. And the other one I like is to go and get a big weight, okay? So, here is a nice big pendulum. Yeah, there we go. Now, what I've done by lifting it up is I've given it some gravitational potential energy. When I let it go, that will turn into kinetic energy. As it starts to rise on the other side, it'll turn back to gravitational potential energy. But the point being, the pendulum can never get more energy than I originally put in. And in fact, because of friction, some energy will actually be dissipated, to use the technical word, to the surroundings as heat. And so the pendulum will never get as close to the iPad now on its way back. Okay? So let's have a look at that. I'll let it go. It will not hit the iPad on its return, even though I touch it against the iPad now. There you go. Just cover it the camera. There it goes. Here it comes. Oh, I must admit, I did think that was going to hit at one point there. Okay? So, there you go. Conservation of energy. You always get the same amount of energy out as you put in. The reason this ball didn't actually return to the original height was, as I say, some of its energy, its gravitational potential energy it's got now, turned into heat as it was moving, because it's moving through the air, so there's friction. It's connected to the ceiling as well, so there's friction of the string there. So it's lost some of its gravitational potential energy as heat, so never quite reaches the same height back. Okay? So, what you can do, if you really want, for a bit of fun, really get close to your monitor screen for this. Yeah? Really see if you can stand the test of nerves of the pendulum coming back at the screen, and see if you can not move as it does this. This is something I do with students in class, and most of them don't believe that it's going to actually work, but I promise you it does, and it doesn't hit the screen. If it did, I'd have a big problem, because I would then have to buy a new iPad. Okay, so here we go, get right up to the screen. Let's see if we can do this pendulum trick carefully and convince ourselves that it will never get back to the same height as it starts off at. Are you ready? 3, 2, 1, go. Ah! And yes, that is the most childish thing I've ever done, including cutting out a face mask in my lunch hour simply for that rubbish joke.